Firstly, let me briefly introduce the application of machine learning in oil and gas industry. So oil and gas industry is composed of upstream, midstream, downstream. So upstream is oil production and exploration. So one typical application of the machine learning and upstream is using computer vision to identify salt body in seismic data. And the midstream is about the oil transport and the storage. So the machine learning can help optimize these processes. And downstream is about oil refining and the sales. Some application of the machine learning like pricing and also supply chain optimization. So our project is about the upstream. The title is steam flood optimization. So firstly, let me introduce what steam flood it is. So the heavy oil is very difficult to be pumped out. The one solution is inject steams to dilute it, and so it can be easily be pumped up. So now the question is, with given amount of steam, how to allocate these steams so that we can maximize the oil production? That's the question we will address in this project. Here is an architect of this system, which is cloud-based. We can see all the data from the field are collected and then transported into the cloud. Then the machine learning algorithm is implemented in the cloud, and also there's a user interface is developed in the cloud so that the user can get access to this user interface easily from the laptop or smartphone to explore the data and also plan the future allocation from this system. So here's the architect. And next one, let me introduce what's the difference between traditional approach and the machine learning approach. So the traditional approach is built on physics-based reservoir model. This model can predict the future oil production based on some historical data and also some future plan. But there's some considerable discrepancy between the real oil production and the prediction. So machine learning approach works in another way. Machine learning model, which is unknown at the beginning, just using the historical data, historical input, as well as the historical oil production to train a new model. So this new model can also be used to predict the future oil production based on the future plan and also some input data for future. So that's a big difference. And the next one, this is workflow. So workflow is composed of four parts. First one is data engineering, and then next is model building, and then data visualization, and the last one is the optimization system, which was used to recommend the optimal scenario for the users. So first one is data engineering. Here is a basic data structure. You can see it is a very typical time series data. The first column is the data, and also there's two groups of wells. One is a production well. Oil will be pumped out from the production well, and the other one is infill well, where the steam will be injected into the infill wells. So we can see there's some features called well status, it's pump or shut in, and also there's some sensor data. Here, I just give one column. Actually, there's at least more than 10 columns, which including some features, some pressures or some temperatures. And for infill wells, there is one column called steam volumes. You can see here is called 6 or 9. That's the steam volumes. And here, oil volume, which is a target we try to predict, which is the big Y here. And the next one is about the data engineering. I will not spend too much time here. So if you are interested, you can refer to our paper. I will give the link later. So basic idea is after the data engineering, there will be two features. First one is yellow one. You can see yellow one is historical data. We just assume here we can see it's today. All the historical data will be marked by yellow one. And the green part is the future plan. So in other words, as long as you have this kind of model, you can change the future plan, which is marked in green part, and then you can predict oil production given different scenarios. So here is the basic idea. After data engineering, we'll go to the model building part. Here, after test a couple models, we select XGBoost. So XGBoost here, the most important reason is XGBoost is a tree-based algorithm, which can be easily to be interpreted. And for example, here we can provide the important study, and the users are very interested in this important study result. For example, they will know which sensor plays more important role in the oil production, like which kind of temperature or which kind of pressure. And also they will know, they have idea which time lag is more important than others. For example, after we inject the steams, usually 2 months or 3 months delay is very important. So that's one very important reason why we select XGBoost. So after this one, here is the result. Here is a 1 month model. I just give an example. So the x-axis is time, months from 2014 to 2018. And the y-axis is a normalized monthly oil production. The blue dashed line is a real oil production, and the orange one is a predicted result. The band is a relative error within plus minus 10%. So left is the training data. We're using the time series cross-validation to select the best model. And the right part is the test data. From here, we can see in the test data, all the predictions are located within plus minus 10% relative error band. On the top right is metric tables for training data and the test data. The metrics we used here, the first is the rule mean square error, and the second one is the R square. You will see there's one called the baseline model metrics. So baseline model, we're just using some simple forward copy. For example, this model is a 1 month model. We just using the oil production today to predict the oil production in 30 days. So just copy there. So that one is a baseline model. Our model, you can see, beats the baseline model, which make us more comfortable about this one. At least it need to beat the baseline model. So here is the result. So last part is optimization. So optimization, as I mentioned before, this one. So now we have this model, and we will go through all the possible scenarios inside this green box, so that this model will give a prediction. You can, let's take a look at the right part. This one is a heat map. It's oil production in terms of the one is in field well 1 and the other in field well 2. So let me explain this one a little bit more. So this pad, there are 3 in field wells here. In field well, I mean steam need to be injected into the steam in field wells. So since the sum of these 3 in field wells contribution should be 100%. So in other words, there are 2 independent variables. So that's why I can plot the right plot. We can just make the in field well 1 and the in field well 2 numbers, and the in field 3 will be 100% minus these 2. And in the table, the middle column is the real scenario. We can see the 100% injection, 100% steams are injected into the in field well 2. And the observation production is about 4,200. So this real case is corresponding to the right corner in the right plot inside that dashed circle here. And when we go through all the possible scenarios, we find the maximum peak, which inside the solid yellow circle, which is optimal scenarios. This optimal scenario corresponding to the right column here, which is means 27% go to in field well 1, in field well 1, and others most go to in field well 3. So this based on this optimal, the predict oil production is about 4,300, which is about 3.3% uplift compared to the real oil production. So we already recommended this one to the user, and the user is this new optimal scenario is being tested. So some preliminary result looks promising, so it is still under testing. Here is optimal themes. And the last one is summary. First, we design a machine learning time series workflow to predict oil production in some specific steam flood scenarios. And then also based on this model, we can recommend some scenarios to user to improve oil production. And the third thing is that this workflow could be extended to other scenarios. For example, the predictive maintenance. And this work has been accepted by the first AIoT workflow workshop at KDD International AI Conference, and I gave the presentation in Anchorage this August. And here is the paper link. So if you are interested, you can just find more details in this paper. That's all. Thanks. Any questions?
Thank you. We have time for a couple of questions.
Thanks, great talk. I'm just curious that for your monthly production, you try to predict 1 month later, 2 months later.
Yes.
Is it one model, or you have a target that's predict all those targets simultaneously?
Good question. So in the example I showed here, there's one model, but we build one model for each pad. So for example, in one pad, there's about 50 production wells and about 5 infill wells. For each pad, we have one model.
I see.
Yes.
And have you explored other algorithm? Because like gradient boosting is not essentially capture the time series structure.
Yes, we tried XGBoost, we tried random forest, and we tried LSTM. And the performance, random forest and XGBoost is comparable, and both of them are much better than LSTM in this case. And the reason why we select XGBoost instead of random forest is because XGBoost has a GPU version which can train the model much faster than random forest. Yes.
Thanks.
Thanks.
Yes, over here. In your importance of features plot, you're showing there are 4 sensors, and you have a sensor 2 on the top of the other sensors.
Yes.
Could you explain that? Why there are other sensors that are below in importance with respect to the sensor number 2?
That's a good question. To be honest, the domain experts, they have similar questions. And that's the reason why they want to have this decision tree model. And then when I show this result to them, they said, OK, looks kind of makes sense, but they didn't have good explanation for why this sensor is more important than others. But they just want to have an idea which sensor plays more important in the prediction.
Does it have to do with the location of the sensors, or?
Yeah, maybe. But at least the domain experts, they didn't share this experience with us.
OK.
Yes.
The other quick question was about the contrast. When you compare the 2 wells, it looks to me that the objective function looks a little bit, quite linear. I don't see high nonlinearity there. So could you explain why it's looking like that? I mean, I know you could find the optimal, but it looks to me very linear.
Yes. That's one observation, yes. Yeah, thanks.
Last question.
Thank you. Interesting, very interesting presentation. My question is not so much to do with the data science part of it, but just your experience in scaling this inside ExxonMobil.
Okay.
How many wells are you able to do this with? Do you have issues with our experiences? There's issues with accessing data from the OT environments and the internal protection and security and bureaucracy, and also some of the tech debt that is built in actually implementing these things on a well-by-well basis, which allows you not to scale rapidly. Just curious to see what your experience was. So.
Okay, for this project, actually it's for one field. So sorry, I cannot release that name of the field, but in that field, as far as I know, there's at least more than 50 pads. So one pad, as I explained to Zhang Chen, so one pad is typically has about 50 production wells. So basically that field will have more than 2,000 wells. So that's the scale for this project.